So hi everyone, let's begin. Today we have the second lecture in our mini course about some modern generative AI models based on flow matching, diffusion bridge matching, and some related topics. So just as a reminder, my name is Alexander Korotin. So previously we had a lecture about flow matching, which is I would say, one of the most standard paradigms to solve generative modeling problems and to generate data. What we are going to discuss today, we are going to discuss another topic, which is not that widespread as the flow matching itself. It is maybe less popular, but it is very natural because it is usually applied to some specific downstream problems, not just to general data generation. And these problems are usually called domain translation problems. And actually, during the lecture, I will also explain what is that. Yes, so don't be afraid. This will be explained. So let's begin. Actually, the plan of our today's lecture is as follows. So first of all, we are going to again go through some basics of diffusion models, because our today's lecture is even more related to diffusion models than the previous one. Yes, and we'll need to better understand some basic concepts than it was needed yesterday. Yeah, so we are going to discuss what are these domain translation problems that we are going to talk today about, how they are formulated, what is the difference of these problems between the standard data generation that we discussed previously. Yes, and finally we are going to discuss the bridge models or diffusion bridge models in different existing variants and how they can be applied to solve the domain translation problems. First of all, let me again say to all of you that most of modern generative models are usually based on diffusion models or their variants, and specifically all modern text-to-image generative models, for example, like Stable Diffusion, GPT image, Kandinsky, and so on, are based either on diffusion models or on flow matching or their variants combined with some other techniques from the field of generative modeling, which allow to, for example, speed up them or improve them from certain perspectives, such as generative adversarial networks. Yeah. So this original paradigm in generative AI, which appeared in 2014, generative adversarial network, it still exists, and nowadays it is kind of used usually jointly with the framework of diffusion models that we discuss during our mini course in different variants. And what I'm going to do now, I'm going to give a very quick but still a little bit more detailed recap of diffusion models than yesterday. We will actually need this because today we are going to talk about specific case of diffusion models, like sub-case, yes, which is called diffusion bridge models. First of all, when we talk about most generative models, yes, they usually apply to the problem of unconditional data generation in some simplest form. Yeah, so with this problem, we have some data set, yeah, and we would like to create some new data which is similar to the training data. Yes, and this is the simplest variant of the generative modeling problem, which in practice, of course, is used in much more complex settings, in conditional variants, when you just want to generate not some random data, but some data corresponding to your input condition, some text user prompt or something like this. Yes. And in previous lecture, we spent a lot of time discussing how to solve this particular problem with flow matching. Yeah, we formalized this problem a little bit in the sense that we assumed that, okay, our empirical data, which we have for training, is not just some arbitrary data, but we assume that it is some data which is randomly sampled from some unknown probability distribution P star, and the goal, in fact, is to use this empirical data to reconstruct this distribution P star, in the sense that we wanted to provide some procedure to sample from this unknown probability distribution. At this point, you may ask, okay, why do I recall this? Why do I recall this problem formulation? Because today, later in our lecture, we are going to discuss domain translation problems, when you have not just one sample of data, but you have two samples of data, yes, and you have to do some manipulation with these two samples. So I just recall this basic formulation of unconditional data generation problem in order for you to just recall our previous lecture and try to compare our today's thing that we're going to discuss later and what we discussed yesterday. Now let me recall diffusion models, but do this in a little bit more detail than it was done previously. Yeah, because previously we just discussed diffusion models, they noise the data, and you just try to learn somehow this process which denoises the data and use this process for data generation. And more or less everything I told about this is that this is based on stochastic differential equations, right? So in our today's lecture, we'll work a lot more with stochastic differential equations. So I'm also going to give a very, very brief recall of their basic concepts as well. So specifically, we are going to work with stochastic differential equations of this type. Yeah, so we have it is written in this differential form. What does this mean? In fact, this means that we have some process, yeah, which evolves in time, and this evolution is described by two things. So the first thing is just some movement along some vector field. It's usually called the drift field or drifting field or vector, speed vector. This is the same as we discussed in the previous lecture related to ordinary differential equations. Yes, because if we just drop this diffusion term, then we just have deterministic movement along some speed vector. This additional term, which is usually called the diffusion term or the volatility or noising term, is the following. It actually means that when we move according to our vector field, yes, as in ordinary differential equation, we add some noise to our movement process so that our movement is not just deterministic, but it becomes stochastic. And the stochasticity is defined by two things. So first is, what is this DWT? Basically, DWT is the differential of the standard Wiener process. So standard Wiener process is just the standard Brownian motion, standard random walk on continuous Euclidean space, yes, which I hope everyone knows from the standard courses from probability theory or stochastic processes, yes, and this term G depends on time. It is like the amount of noise which we input to our movement process at time t. Yeah. So what this plot shows? Actually, this plot shows more or less how the standard Wiener process looks like in one-dimensional space, how it evolves over time. Yes, so this is like time, this is like space axis. Yes, this is the process value. If we talk about it in one dimension, so this is more or less the standard random walk, which corresponds to the stochastic differential equation where f is equal to 0 and g is equal to 1. So this is like dxt equals to dwt. So what this expression means informally, I actually explained. Yes, so we move according to the vector field. Yes, and we input some noise to this our movement process. And this expression means that our initial start of the process is at some probability distribution P0. Yeah, but usually this is formalized in the integral form, which means that, okay, if we want to obtain the process value at time moment t, yes, and we start at some point x0, then to obtain this value, we just need to compute these two integrals. So basically this, what is actually complex about these two integrals is that this integral, in fact, depends on the previous trajectory, right? So usually taking such integrals is not trivial. This is like standard Lebesgue integral. This is the integral when we take the integration with respect to our value of our random process. So why actually I am recalling this? I am recalling this because diffusion models are based on stochastic differential equations. Yeah, diffusion models, what they do? Suppose that we have some complex data distribution. So this is just simple one-dimensional example, but it is very illustrative. Suppose that you have some like two model distribution, yeah? What is the standard way how diffusion models work? First, we pick some particular stochastic differential equation which describes some evolution of points in this distribution. And we pick such stochastic differential equation, it's usually called the forward process, yeah, that gradually destroys the information about the data. So basically it noises the data so that our initial distribution gradually turns to some simple distribution, such as the standard Gaussian distribution, from which it is easy to sample, from which it is easy to get random samples on your computer. Yes, and then the main idea of diffusion models is for this forward stochastic differential equation just to derive the reverse stochastic differential equation, which allows to model the same dynamics but in reverse time. Yeah, when we move from our simple distribution to our complex distribution by the same process but in reverse time. From the general theory of stochastic differential equations, there is a known fact that the reverse stochastic differential equation can be written through the forward stochastic differential equation, and it is given here. But there is a misprint. Okay, this is okay. So the key difference between the forward stochastic differential equation in the backward stochastic differential equation is that in the backward stochastic differential equation, which describes this process in the reverse time, is that there is one additional term appears, which is in general unknown. So what is this term? This term is called the score function, and this score function, what is it? It is a gradient of the logarithm of the density of the process at marginal time moments. So basically, if we take a look at our process, we just need to consider some slice at some time moment t and the density of this slice. And this will be the density of this slice. So this is the density of the marginal distribution of the noisy forward stochastic process at time moment t. Yeah, so this means that if we want to do data generation, basically going from simple distribution to complex distribution by reverse stochastic differential equation, then we need to somehow compute or reconstruct this unknown term. And in practice, this unknown term is usually reconstructed with neural networks. Yeah? So again, the main idea is as follows. We pick some data noising process which destroys the information about our data and converges to some simple probability distribution at some long time horizon. Then we just try to get the reverse stochastic differential equation. For this, we need only to obtain this unknown score function. And the thing is that a natural way, okay, how to get this score function? Well, it is not analytically tractable usually, yeah, because, well, first of all, you don't have the entire input distribution even, yeah, you usually have only samples. So an initial way is to try to approximate it with a neural network somehow. Yes, this is very similar to what we discussed in flow matching. In flow matching, we approximated the vector field. Here we also approximate also kind of vector field, but it is this unknown score function of the marginal distribution of our stochastic process. How to do it? Well, a natural approach is, okay, we want to get some unknown value. What we can do? We can do regression on this value. Yeah, just direct regression. So this is may look a little bit complex because, well, we do some integration over time, but this is very natural because we need to reconstruct at different times. Yes, and we take expectation with respect to our process to just cover the entire space. Yes, but in fact, what we can do the regression on the value which we would like to get. But the problem is that this very naive and straightforward approach is not tractable, yeah, because we do not know this value. Yeah, if we know this value, why do we need to regress some neural network on it to reconstruct it? Yeah, so it's just unknown. So although this looks very natural and recovers the true score function, this optimization is infeasible. So what typically people do in diffusion models, they slightly change this objective, and this is completely theoretically justified. So they replace this unknown score function here in this objective with the conditional score function. Basically, this is the score function of the probability density at point xt given the initial point in which the process started. I'm not going to dive in a lot of details like why this works and why it appears, but I will going to say two things. That first, the general logic here is very similar to what we seen in flow matching. In flow matching, we actually regressed some vector field onto some conditional velocity direction, given two endpoints like x0, x1, which was tractable. Here the logic is very similar, so we regress our neural network onto some conditional object which is tractable, and this object is tractable because this is the score function of our direct forward conditional noising process, so we know how to noise the data because we usually a priori choose some specific noising process for which we can derive everything like moments, conditional distribution, and so on. But the main point of this slide is that we do some regression objective to learn our score function of a neural network, and then when we learned, we do data generation. And this slide is the same slide as in the previous lecture, explaining how the data generation in diffusion model works in the simplest way. When you do this generation by modeling your backward stochastic differential equation, again, when you model your backward stochastic differential equation, first you replace this unknown score function with your trained neural network, and then you model this numerically, usually by some numerical integration schemes. The simplest one is just the Euler-Mariyama, when you just discretize your time grid and do this simulation. And again, one of the problems of diffusion models which we discussed previously is that to generate new data, you need to make a lot of steps in this numerical integration, and this numerical integration step is very complex and challenging because to just compute this one expression, at each step you need to evaluate your neural network and get the outputs of the neural network. So this is why in diffusion models the term which is called number of function evaluations appeared, which usually means that how many times do you need to apply your neural network to just simulate your denoising process and get clean data. Okay, so previously, in the previous lecture, there was some question. Okay, but how do these models work in the conditional case? Because previously we discussed, when we talk about flow matching, just the problem of unconditional data generation. When you just need to generate some random data corresponding to your given data. But in practice, what you need to do, you need to generate some data which corresponds, for example, to your text prompt, like text to image generative models like GPT image, Kandinsky, and so on. So how it works and which modifications to the base model need to be done to make it conditional? Well, there are several ways to do this, and one of the main straightforward ways that we'll use today during our today's lecture is just straightforward conditioning. So roughly speaking, suppose that you have several conditions. Why? It can be like text prompts, for example, right? So just cat sits on the table, I don't know, dog flies in the air or something like that. How to learn a model which is capable of generating something which corresponds to your condition? Well, the natural approach is just, first of all, you need a paired training data set, basically condition and some image which corresponds to this condition. And secondly, what you do, you just learn a family, in fact, of denoising processes, right? In practice, this is done just by training a single neural network, which represents this unknown score function for denoising process, but for all conditions simultaneously. So depending on which condition do you put to your model, which text prompt, this will result in like different generation corresponding to this condition. And this reverse, so roughly speaking, you train a lot of denoising processes for different conditions simultaneously, and then at generation stage you just use the one which corresponds to the condition which you input to your model. And this is done by two things. So first you need a paired training data set like condition and sample corresponding to this condition. And second, you just need to modify your loss slightly, because in your loss you need to put both condition and both sample. We'll talk about this in more detail, but not in the context of just general diffusion models, but in the context of diffusion bridge models next. Okay, so this is the end of preliminary part related to diffusion models. And now let me go to diffusion models for domain translation problems. But before that, let me explain you what is domain translation problem and what this word usually means. So domain translation usually means the following. So previously we worked with one empirical sample and we wanted to generate this empirical sample from scratch. Yeah? But in practice there are a lot of tasks when you have two empirical samples and you need to do something with them. Yeah? Usually like one empirical sample from one domain, another empirical sample from another domain, where the word domain here means kind of set of objects with the same characteristics in some sense. Yeah? These type of problems, where they appear, when you need to like take samples of one type and produce samples of another type, they are actually widespread. And one of the most widespread applications of this is image enhancement, image restoration, and image super resolution. Yeah, for example, most of modern smartphones do some kind of image enhancement by AI in their camera. Yeah. Another type of related problems to this is style transfer, modality transfer. So this is a like just model example, but roughly speaking, the same problems appear in many applied scenarios as well, related to weather modeling, in medicine, and so on. So what is the main difference between domain translation and just arbitrary generation? Yeah, because here you have some input object, and with your diffusion model you need to kind of modify this object so that this object will become the object from the second domain, which corresponds to this object from the first domain. And when such domain translation problems are considered, there are usually two variants of these settings. Yeah, one setting is so-called paired setting or supervised setting, and another setting is unpaired or unsupervised. What is this paired setting? In paired setting is the following. During training of your model, you have sets of pairs of samples from input domain and target domain. So in the machine learning language, this is just a standard supervised learning problem. And unpaired or unsupervised case is the case when you just have samples from input domain and just have samples from the target domain. And you still need to learn some meaningful translation function, map, neural network, whatever, from one domain to the other. Of course, this problem is not very well defined, and this makes additional challenge in solving this problem. Because usually you cannot clearly like guarantee what are the properties of your solution. But we'll talk about this in a more detail a little bit later. So, okay, how diffusion models can be applied to all of these problems, paired or unpaired. So first of all, let's talk about paired case. How diffusion models can be applied to the paired case. But roughly speaking, they can be applied in the following sense. The same way as they applied for text-to-image generation. So in fact, text-to-image generation can be viewed, in fact, as a paired domain translation problem, because like your first domain is the domain of text, the second domain is domain of images, and you need to, for each text, to provide an image which corresponds to this text. So we can just apply conditional diffusion models to solve paired domain translation problems. This is widely used, for example, for image super resolution, when you usually can create a lot of synthetic pairs. That is, your condition is a low resolution image, your target for diffusion model is the high resolution image. And what you do, you just train conditional diffusion model objective. So what is this conditional diffusion model objective? So you train your neural network, your score function, to regress to get the true score function, and your neural network has additional input, condition on the input low resolution image. And this loss, in fact, is just the standard diffusion model loss, but in the conditional regime. Yeah, so there are two changes from the standard unconditional loss. First, you add some additional integral or expectation with respect to conditions, yeah, because now you need to kind of train a lot of models in some sense for different conditions, yes? And your score function becomes conditional. But when you manage to solve this regression problem, you can do conditional generation in the sense that for each input image y, you know the score function of the data denoising process, and you can model it numerically by the Euler-Mariyama scheme. So this is how the inference in such models works. So you just put your low resolution image as a condition, this y, yes, and you model your diffusion process, denoising diffusion process, this one, by some numerical scheme like Euler-Mariyama, and in the end, you obtain not some random image, but some image which corresponds to this low resolution condition, because your score function, your neural network, which you learn, is conditional one. Okay, but this is about pair setting. Yeah, when you have pairs and what to do with this, you can just train conditional diffusion model for this case. But what about unpaired case? If you do not have pairs, what is the main problem with unpaired case? In fact, all these conditional diffusion models are just not applicable for unpaired case. Why? Because to train your model, you need pairs. But in unpaired setting, you do not have pairs. You have either, for example, low resolution image or high resolution image in each pair. And if we get back to these slides, then we'll see that in this case, we need to have pairs, because y is like input sample and x0 is target sample, which corresponds to y. So this loss is fully paired, and we cannot use it in a pair setting. So a short story is that, first of all, diffusion models cannot be used in unpaired setting. And in fact, you might ask a second question, which is very, very, very natural here. Okay, we do generation, even in the conditional case like this, we do generation by diffusion model, yeah? And we do generation from pure noise. Well, it is a natural question. Okay, why do we do generation from noise? Because we already have some meaningful input sample which contains a lot of prior information. Yeah, and we use this information only as a conditioning for our denoising process. Can we do something better? Maybe we can directly start our denoising process from this image. Why do we start from image? Maybe it is expected that it will be faster if we start from just some already meaningful image with content, yeah? And today we're going to answer two questions. So first, how to learn diffusion models, which start directly from data and generate some other data. And second question is how to apply diffusion models for unpaired domain translation problems, where the standard diffusion models cannot work because, well, it's not clear how to learn it. Yes, and this is called the diffusion bridge models. Well, it might look very more complex than what we discussed previously in flow matching lecture, but actually I hope that you will understand that this is just a very, very slight extension from flow matching that we discussed previously. What is the key difference? The key difference of this diffusion bridge framework that we are going to discuss from the diffusion models is as follows. First of all, diffusion models, they typically start generation at noise and end at data. Yeah? And in contrast to it, diffusion bridges, they can start generation at arbitrary distributions, like flow matching. Yeah? And this is why they can, in fact, be applied to unpaired domain translation problems. We'll see about it. And how they can be used to start data generation directly from some meaningful input prior samples. Okay. So this is the main literature related to our today's presentation. So in fact, the first paper is a paper which introduced these bridge matching models 4 years ago. And interestingly, so last lecture I told you that, okay, flow matching was invented not by the authors of flow matching, which I showed you on the previous lectures. Yes, so this guy actually invented everything 1 year before everyone else reinvented it. But unfortunately, this paper is unknown. Like only a few people know about this paper and about the existence of this guy at all. But this is reality. Okay. What is diffusion bridge? So I'm talking about diffusion bridges, and our lecture is about diffusion bridges, but so far I have not even explained what is that, because we haven't used it yet. So what is a diffusion bridge? So diffusion bridge is a particular case of diffusion process. Yeah? Suppose that you have some diffusion process of this kind. For example, it can be standard forward noising process from any standard diffusion model. Yeah? The standard variants are like variance preserving, stochastic differential equation, variance exposing. We'll talk about it in a few slides. What is a diffusion bridge? Basically, diffusion bridge is the same process, but conditioned on the start and end points. Roughly speaking, we can consider this diffusion bridge as a distribution on the trajectories. Yes? And we take this distribution on the trajectories and ask the question, what will happen if we condition this process at the start and end points? So that this process, what happens if this process starts at some particular point x0 and ends at particular point x1? Yeah, what is the distribution of this process, assuming that it starts at one point and at another point? And this will also be a stochastic process. And furthermore, this stochastic process will also be described by some stochastic differential equation. Yes? And the main point is that this is not just some arbitrary stochastic differential equation. So this, first of all, why it is called a bridge? Yes, I think it's very natural because it kind of bridges 2 points. Yes, so it's conditioned on 2 points. How it is described? Well, from the theory of stochastic processes, there is a well-known result, which is called the Dubs H transform, which gives like the explicit formula for this stochastic process of the diffusion bridge. So it is actually described by stochastic differential equation in which the drift term is similar to the drift term of the original process. The noising term is also similar, but there is one difference. So there is some delta in the drift term compared to the original process. But this, which is very natural, because this actually this difference, it makes this process end at particular point in time. Yeah, so this is what makes it a bridge. You see that this formula is very similar intuitively to what we discussed related to reverse stochastic differential equation diffusion models. There, to obtain the reverse stochastic differential equation, you also needed to add some term to your drift. Here, this term is different. Yes, and the kind of idea of what we're doing here is different. Here, we are going to make our stochastic process to condition on some start and end point, and basically this delta term gives the condition on the end point. So this stochastic process will end at point x1. Throughout the lecture, we will actively use the standard Wiener process, yes, with, actually not standard, but with some rescaling of its variance, yes, so this square root of epsilon is just the standard deviation of this Wiener process, so rescaled, yes, and we'll use the notation of Q to denote the distributions, like the joint distributions at several time moments of the stochastic process, like marginal distribution at time moment t, joint distribution at 2 time moments, condition, and so on. So the main point of the slide, we have some stochastic process. What we do with it, we consider for this stochastic process Q, capital, we consider a lot of stochastic processes Q when conditioned on x0 and xt, when we make from this process a lot of different diffusion bridges, yeah, by conditioning this process on different start and end points. Then, what are we going to do? In fact, it may look very, very complex, what I'm explaining now, but I hope in few slides you will understand that this is a very slight extension of flow matching, in fact. Yeah, it may look not very obvious, but it is. What we are going to do? What we are going, suppose now that you have 2 data distributions, P0 and PT. Yeah, so why I say PT, not P1, as previously in flow matching? Well, this is just because many papers in this diffusion bridge paradigm, they use notation T capital, like the end time. Well, you can think for simplicity that it is just equal to 1, but it does not make a lot of difference, yeah? So what we're going to do? We're going to build some stochastic process which interpolates between two probability distributions. Yes, remember in flow matching, we kind of build this interpolation sequence of interpolating distributions. Here we're going to do roughly the same thing, but from a different perspective. We're going to consider the following thing. Suppose that you have some coupling of two probability distributions, so like input data and target data. And you have some coupling between input and target data. For example, it can be just independent, like product of distribution of one data and another data, or any other. Yeah, we'll start with just general couplings. And we are going to build the following stochastic process, which is called the reciprocal process. What is that, basically? It is a process whose trajectories are defined in the following manner. So we first take some random point to a pair of points x0 and xt from our coupling of two probability distributions, and then inside this pair of points we kind of insert our diffusion bridge. So roughly speaking, to get the trajectory for this process, we need to first sample start and end points from our data distributions, and then connect them with the trajectory from the diffusion bridge. This is very, very similar to what we discussed in flow matching, but in flow matching, we kind of sampled 2 points from input and target and connected with them with a straight line. Now we allow to just connect 2 points just by some arbitrary diffusion bridge process. That's it, which is like more complex, but at the same time it is more general. And this notation defines the reciprocal process, which means that our process is a mixture of diffusion bridges. Mixture in which sense? We have a lot of diffusion bridge processes conditioned on different points. And we just take their mixture with respect to some coupling of two probability distributions. This directly means that to sample from some trajectory from this process, we need to first sample a pair of input and endpoints, kind of choose the component in our mixture, and then connect them with diffusion bridge. Yeah, so again, so what we did, we constructed some stochastic process which interpolates between two probability distributions, P0 and PT. Yeah, but this is very similar to flow matching when we constructed this sequence of interpolating probability distributions. But so far, this sequence, this process is not very useful for us. Yes, we cannot use this process, for example, for data generation. Yes, so that if some point from one distribution comes, we do not know how to use it to create a point in the second distribution, because to simulate the trajectory, we need already to know the end point by the construction. Yes. So the question is, how can we transform this stochastic process to something which is more tractable for our generative modeling needs, so that we will be able to sample just the start point of this process and model the process somehow to get the end point, so that they get the point from the second distribution of data. So this is again how it looks like. So we have two distributions, we have some coupling between them, we sample random points from this coupling and connect them with trajectories of the diffusion bridge. So roughly speaking, this is the same as in flow matching again, but our connection rule, let us call it this way, is a little bit more complex, because it is now described by stochastic differential equation. It is itself a diffusion process, not a deterministic movement according to some line. And there is a very, very important thing, which is like one of the main things in our today's lecture, is that how to make this process generative. Generative in the sense that we will be able to take points from input distribution and transform them to some points in the target distribution. And this is done by the following thing, which is called the Markovian projection. So that is a very, I would say, complex concept, but it has a very intuitive explanation. So what we're trying to do? We have some process, which is in general not Markovian. Yes, so to simulate it, we first need to know the start and end point, and then simulate the trajectory between these points. But we want, for generative modeling, need some Markovian process, which means that we want to just take some input points, somehow model it step by step, and get some endpoint at the end. How to obtain some Markovian process, which is useful for generative modeling, from this original reciprocal process. This is done by the tool. It is a mathematical tool, which is called the Markovian projection. It is a very, very, very general tool from the theory of stochastic processes, and in fact it can be applicable not only to this class of reciprocal process. It can actually, you can consider Markovian projection for more or less any reasonable stochastic process. What it roughly tries to do, it tries for a given process, which has some properties, obtain some other process which simulates the properties of the original process, but at the same time it is Markovian. So in our case, it is represented by some stochastic differential equation. And if it is represented by some stochastic differential equation, then, and if we can learn this somehow from data, then we are fine, because we will be able to do data generation. So we will be able to take points from input distribution, just model this stochastic differential equation, and obtain some points at the target probability distribution. What is this Markovian projection? In fact, this Markovian projection is given by this formula. So this is quite a complex theory from like 30 years ago or something like that, that there is a process, this is formulated in our particular case when we work with reciprocal processes, and we do Markovian projection for these mixtures of diffusion bridges. So the main point is that there is a process which is called the Markovian projection, which is in the forward time, that when we move from left to right, given by this stochastic differential equation. And this stochastic differential equation gives the process which, first of all, let's try to understand this formula. What is going on here? As you may note, first of all, this formula is a lot similar to many other formulas which we have seen previously. For example, the formula of reverse stochastic differential equation and the formula of the diffusion bridge. So they all had one very similar aspect. They have the same drift component, part of drift component, yes, which is the same as in the original noising process. And they have the same noising term, so they do not change. What changes is some delta to the drift. So what I say is that the Markovian projection of a reciprocal process, which you constructed a few slides ago, is this expression, where in this expression, this delta is defined as follows. So it is an expectation of our reciprocal process when we have when this is like intermediate point and this is the end point. So suppose that we want to compute the drift of this process, yes, at some point xt. How can we do it? We need the drift of the original process plus some delta, and this delta is defined by the expectation of the end point of our reciprocal process given our current point, yes, but of this term. And what is this term? This term is the same as appearing in the Dubs H transform, so the drift of the bridge process. How to interpret this? For all bridge processes, you have some drift. Yes, and when you do Markovian projection, you kind of average the drifts of all processes which go through this point. This is the same as in flow matching. To compute the vector speed direction in flow matching, we needed to average a lot of things. Yeah. Here we also do the same, but in a more complex way, because now we work with stochastic processes. We kind of average slightly different thing. We average this part of diffusion process drift, yes, which is given in this conditional process. And the same problem appears in flow matching. In flow matching, if you may remember, when I gave you the theorem, there was a closed form expression for this drift. But it was not tractable. Yeah, because to obtain the closed form expression of drift in flow matching, you had for an intermediate point to sample endpoints from which this point comes from. But you cannot do this. In flow matching, you can only sample the intermediate point given endpoints, right? Here the situation is the same. Although this is like theoretically true, yes, but this thing is intractable in practice because you need to take expectation of your reciprocal process, basically this process, yeah? When you need to sample the endpoints of this process given the intermediate points of this process. But you cannot do it. You can do only the reverse thing. You can only sample intermediate point given endpoints. Yeah? So this is, again, theoretically correct, but practically it is intractable. Fortunately for this, there are some ways how to learn it. But before discussing this, let me explain one more thing, which might look very complex, but what is the message here? The message is, okay, when we work with ordinary differential equations, like in flow matching, what we have? We have some movement along the vector field, which is deterministic movement in forward time. If we want to simulate the same movement, but in backward time, what we need to do? We just need to take the same speed vector, but with minus sign. Yes, because if we go forward with like v, backward we go with like minus v. This is obvious. But in the case of stochastic differential equations, this is a little bit more tricky. If you want to simulate the same stochastic differential equation, but in backward time, it's not straightforward just taking minus v. Why? Because we have already seen this in basic diffusion models. Yes, when we wanted to learn the backward stochastic differential equations, there was some unknown term, yes, score function, which we learned. So roughly speaking, why I recall this? Because when we consider Markovian projection of a stochastic process, we can model it in both forward time and both in backward time. This will be the same stochastic process, but with different representation. And to model it in forward time and to model it in backward time, you need to consider different drift functions. Yeah, so this is why Markovian projection is usually considered in both forward time and in reverse time. Why I'm recalling this? Because many papers related to diffusion bridge models, some papers consider forward time representation, some papers consider backward time representation. So for completeness of the exposition, I'm giving you both. So this is the backward time representation, which differs, in fact, in this drift function. So it's just computed differently. But roughly speaking, it describes the same process, but allows you to model it in backward time. Okay? One thing which I should explain here. So, okay, I'll explain it later. Okay. How to learn it? How to learn it? As I already told you, that the direct drift of the Markovian projection is intractable. Yeah, because like in flow matching. But fortunately, like flow matching, you can design some regression type objectives, how you can learn this drift from your data with a neural network. And these are two objectives which are shown here. One objective is for like learning the drift of the forward process, yes, forward Markovian projection, and one is for learning the drift of the reverse Markovian projection. What we do here? Let us try to understand. So what we do here? Here we sample points from our reciprocal process, like start point x0 and point xt. We sample this from our data coupling, like in flow matching. Then we sample some intermediate point xt from our bridge process. Well, of course, how to sample this depends on the particular type of the bridge process. I will explain it in a few slides, but the main point is like in flow matching. We sample start point, we sample end point, we sample intermediate point, and we do some regression on some score function. And this guy, which is shown here, is actually tractable. We'll see in 2 slides how to compute this and how it is related to flow matching. So roughly speaking, the training logic is here the same as in flow matching. Sample one, sample another, which corresponds to this, yes. Sample intermediate point, and then at this particular point, regress some neural network onto some direction given by your problem statement, by your stochastic process. And this probably leads to the drift of the Markovian projection. Of course, theoretically, if you manage to solve it perfectly. Now, let's take a look at this in more detail. Like, okay, this is learning objective, but it is a generic objective, like how to sample intermediate point from some stochastic process. Not clear. I have not yet explained it, right? How to compute this term? Is it actually tractable or it is not tractable? What can we do? And the answer for this is you just need to open some table which explains you all these formulas. Yeah? Roughly speaking, what this table explains. Suppose that you have some initial process with which you work. Yeah, for example, it's usually called prior stochastic differential equation, which describes your dynamic. Yeah? For our construction, what we need? From our construction, we need to know the diffusion bridge. And for this diffusion bridge, there are, for the most common cases which are used in diffusion models, there are also closed formulas, how to compute this bridge. Yeah? This bridge is also described by some stochastic differential equation, but what is important for this stochastic differential equation, kind of everything is tractable in the sense that usually people consider prior processes to be so-called Ornstein-Uhlenbeck processes of different types. Usually they simplify all this a lot to some kind of linear in drift processes or just even processes without the drift at all. So just noising processes, like when you just add noise to data. Yes, and for all of this, everything is tractable. Specifically, if we go to this formula, here we need to sample intermediate point xt given initial point x0 and end point xt capital. Yes, how to sample it? Fortunately, this is easy for most of standard processes which are used here, because this intermediate distribution of a time point in a bridge process given the endpoints is the normal distribution with some known parameters. Sampling from normal distributions can be done just easily nowadays without any problems. Yeah. Also, this guy which is shown here is also computable analytically for 2 points xt and x0. I think I do not have this particular formula in this presentation, but yeah, but it can be found in these related papers, for example. Yeah, so roughly speaking, everything here is tractable to learn a neural network. Yeah, to regress this Markovian projection drift function. Although it may, of course, look a little bit complex. Anyway, how it works. So this is a demonstration from one paper by NVIDIA, which is called image-to-image diffusion bridge. Actually, even image-to-image Schrödinger bridge, but let's not discuss this yet. What they do, they learn diffusion bridge for different image restoration problems. Yeah, so in image restoration problems, you usually have paired training data. Yeah, so you have like degraded image and restored image. For example, you can do this with for super resolution. For super resolution, well, there are many ways how you can construct this degraded data synthetically, artificially. Yeah? Some other problems related to restoration of JPEG images. So when you do JPEG compression on your computer, yeah, when you compress and decompress image, of course it destroys some information about your data if you use some compression level, yeah. And the goal is to reconstruct the JPEG destroyed image with a diffusion bridge, and as you may see, it works very well. So this is a diffusion bridge model trained directly on pairs x0, xt of degraded data and clean data. Yeah, and this reconstruction is done by diffusion bridge. So after the training, the model takes as input degraded image and gradually improves it until it becomes close to the true expected clean reference image. Yeah? But one thing which is a little bit tricky here, and I actually did not highlight it previously, it is the fact that when you have some data coupling and you learn a bridge meshing on top of this coupling, you obtain some Markovian projection, some stochastic differential equation, which can be used for data generation. Then this projection does not generally guarantee that you will preserve your correspondence between data. What does this mean? This means that, for example, in that previous image restoration problem, if you learn your model on pairs of data, after training, your diffusion bridge model may output not the pair data in the second domain, which corresponds to your input data. So roughly speaking, informally, if you do like super resolution of an image of a horse, well, theoretically, you can get an elephant, yes, as an output. Well, theoretically. In practice, this is not a very big problem. In practice, you can apply bridge meshing models for some image restoration problems, and it works. But usually, people consider some specific extension of these diffusion bridge models, which allows to alleviate this theoretical issue. The theoretical issue is that, okay, you learn on some data correspondences, but at the end of training, what you obtain does not preserve these correspondences. Yeah. So how this issue is solved usually? Yes, and what to do with it. But before discussing this, let's do the following. Let's try to understand how all this is related to flow matching. Yeah? Because previously, when we discussed, several times I repeated you that, okay, this is the same as flow matching, but a little bit more complex. Finally, how it is related to flow matching. The relation is very simple. The relation is that consider a particular case of a diffusion process, which is given by the standard Wiener process. So with some variance epsilon. Yeah. If we consider for training the independent data coupling, so we'll sample from input and target independently as in flow matching, and take a look at our objective, which we obtain, we'll find that surprisingly it is very similar to flow matching. Specifically, what our bridge matching objective will look like. So we will regress our neural network on the known, this expression. For the Wiener process, for this one, yeah, this expression has closed form and it is directly substituted here. Yeah. And how this is like x1 minus current xt divided by 1 minus t. And how our objective will look like. Our objective will look like as follows. We sample input point, we sample target point independently, we sample random time moment, we sample a point from our bridge process at this random time moment, and the sample from the bridge process is sampled the following way. So basically for the standard, for the Wiener process, the Wiener bridge, sometimes it's called the Brownian bridge, has closed form expression, and its marginal distribution from which we need to sample is this. So roughly speaking, to sample an intermediate point xt, we need to sample from normal distribution whose mean is just exactly this linear interpolation between 2 points. And it has some variance proportional to our parameter epsilon, which is the variance of our prior Wiener process. So if we take a closer look at this objective and consider epsilon like the variance of our Wiener process, which converges to 0, so we kind of try to make everything deterministic, no randomness in some sense, right? Then what this will mean? This will mean that we will sample our intermediate point just from degenerate normal distribution. So this will be exactly the point in the connecting line between 2 points x0 and x1, which we sample deterministically in flow matching. And our objective will also degenerate. So because xt will be like with very, very high probability exactly this point in the line connecting x0 and x1, and this will be because x0, xt, and x1 will be located on the same line. This will be equivalent to what we have in flow matching. Yeah, so roughly speaking, flow matching is a specific deterministic case of bridge matching which appears in the limit of bridge matching when we consider linear process prior with decreasing variance, decreasing to 0. Yeah? And this is the relation. And this is comparison, right? So in flow matching, we just learn some ordinary differential equation to map one data distribution to the other by this laws. In bridge matching, in one of its forms, when we consider the linear process prior with some variance epsilon, what we do, we just learn very, very similar objective, but with one additional kind of source of noise, because we now consider not deterministic interpolation, but stochastic interpolation with diffusion bridge, and obtain this loss, which actually becomes the loss on the left when we just consider the degenerate case. Okay? Okay. Finally, let's get back to the problem of the fact that when we train our diffusion bridge model, it may alter the coupling on which we train. So in the end, we have no guarantees that we will obtain the same output object as we expect during our initial data set construction. Okay, how this is avoided? Avoided the fact that when we train our model, we may obtain something unexpected, yes, some other coupling in the end, not the one on which we train. This is avoided by conditioning, the same way as it was done in diffusion models, in conditional diffusion models. So what we do? Previously, what we discussed is the unconditional bridge matching. Yeah, we have two distributions, and we learn a diffusion from one distribution to another distribution using some coupling. But in the end, this diffusion is not guaranteed to preserve the coupling. So roughly speaking, if for training we used some input and target pairs, like this set corresponded to this corresponded to this, after training, it may happen that, okay, for this point, some other set of points corresponds. Yeah, so kind of when we do super resolution of a cat, we obtain elephant, theoretically, yeah? Of course, we want to avoid this. Of course, we want to avoid this. How can we avoid this? Well, ideally, we want to obtain something like this. Yeah, when we learn some diffusion process, and it preserves the correspondences between the data. How this is usually done? This is usually done by just changing one thing in the model. Roughly speaking, this one thing is just adding the condition to your model. So instead of learning just one diffusion process, which transforms input data to the target data, what we do, we kind of learn a lot of different diffusion processes. And each diffusion process maps each particular data point to the distribution which corresponds to this data point. So roughly speaking, we simultaneously learn a family of bridge matching models, and each bridge matching model is designed specifically for this point, to map this point to some conditional distribution of data in the second domain which corresponds to this input point. How this, what changes in practice, yeah? Well, in practice, in fact, only one thing changes. We just add the condition to our speed vector. Well, here, this might be misleading because here it's in expectation it should be also x0 because it is needed to sample XT. But anyway, there is only one thing really which changes. Yeah, so you just add condition to your neural network which learns the drift. And after this learning, you are guaranteed that you will learn a diffusion process that will map your input point to some distribution which corresponds to this point. Because, again, what you do here is you learn a family of bridge machine models. Each bridge machine model is both conditioned on some input point and starts diffusion from this input point and maps this input point to the distribution of data which corresponds to this endpoint, start point. What should be taken into account here? That it is not the same construction as was with Markovian projection. Because in Markovian projection, you just learned one Markovian projection process, yes, which was unconditional, yes, and it had two representations, forward representation and backward representation, which were the same processes but just viewed from the different perspective. In this case, there is no kind of equivalent backward representation. Why? Because by construction, all this methodology is asymmetric. You condition your model on the point from the input domain. Yes, and you cannot kind of, there is no like nothing backward here in this model, because to do some backward translation, you need to condition on the point from the target domain. Yeah, and it will require a separate model for this. Yeah, so roughly speaking, unconditional Markovian projection learns one diffusion process, which can be represented in forward and backward time. Conditional diffusion bridge model learns a family of stochastic processes from like left to right in the forward time, yes. And if you want to go backward, you need to learn a separate model which learns other diffusion processes, which will start at points from the target domain, will condition on these points, and will go backward. Yeah, so why I'm saying this is that because some papers which do conditional bridge matching do it in the forward manner, some papers do it in the backward manner. Yeah. But this conditioning methodology works. So in the original papers which proposed this, they tested this in many problems, including super resolution, but super resolution I skip it because I already explained it. They show that this can be used for some, for example, synthetic Fourier to data generation, like so this is, as far as I remember, unconditional model, so it does not work well. So conditional models that usually work much better, but if you have paired data. Yeah, because to train conditional model, you a priori need to have some pairs. Okay, and the final part of our today's lecture is the following one. So far we have discussed how to learn models in the paired case. Yeah, so if you have pairs of input and target data, yeah, from target domain. In this case, well, we can learn unconditional bridge model, conditional diffusion bridge model, just conditional diffusion model if you want. But the main point is that most of these things are not applicable when we work with unpaired case, when we have only samples from input domain and only samples from the target domain, yes? Because we can just not like even train our model, because for training we need pairs. Yeah, and this makes this case more challenging. But there are a lot more challenges in this unpaired domain translation case, because in fact during training you have no correspondences between samples at all. And in fact it is a part of your job to think about how can we define these correspondences to learn some meaningful model which can be used in some reasonable applications. And the main problem is that there are a lot of different ways how to transform data from one domain to the other, and not all of them are reasonable, right? For example, this model case shows some problems which appear in unpaired domain translation. For example, technically, this domain translation is indeed a translation between two probability distributions. Yes, so you kind of map the distribution of real faces to like distribution of synthetic, distribution of anime faces to kind of solve this style transfer problem. Yeah, but this is actually useless. Yeah, because it's more or less like does some random transformation to the data point to transform it from one domain to the other domain, right? What is actually needed in practice in unpaired learning problems is usually to find some solutions which keep the content of the image. So roughly speaking, that the object which you generate when you do this translation from one domain to the other should reasonably correspond to the original sample from the input domain. Yeah, for example, just consider like some medical case. Yeah, for example, you do some super resolution of like MRI, I don't know, of MRI image of, I don't know, of a brain, yes, and it outputs you a like super resolved MRI image of a leg, I don't know. Yeah, of course this is not reasonable and this is not useful. Yeah, the question is how to find solutions which keep the content. Yes, this is one thing. And second thing, which is very important, is how to formalize this. Yes, because like what does this mean that it keeps the content? Well, of course, there are many ways to formalize it, and usually depends on the particular problem. But what we are going to do now, we are going to discuss like generic recipe, which sometimes works, well, sometimes not, but the problem is itself very challenging. So again, let's recall that for training conditional diffusion-based model, yeah, we were not able to adapt it to unconditional case because we have no pairs. So we cannot train, not clear what to do. In unconditional diffusion-based model case, surprisingly, it can be adapted to unpaired learning case. And there is a methodology how to do this, which is very, very similar to the rectified flow paradigm, which we discussed during our previous lecture. Yeah, when we iteratively applied flow matching on top of previous flow matching, it converges to something. You can do the same with bridge matching, and you can even guarantee that it will converge to some meaningful solution from the perspective of content preservation when you do this translation from one domain to the other. How it works? It works in the following way. Suppose that you have your data distributions, P0 and PT in this case. What you do, you just train your bridge matching model, initial bridge matching model using some independent coupling of data. So you randomly sample input samples and target samples. And what you do, you just learn your drift of your Markovian projection. Then what this allows you to do? In fact, this allows you to do data transport from one distribution to the other, some data transport. It's not yet clear which properties it satisfies, yes, because it just what it does, it just assigns to some point some conditional distribution, which is obtained after modeling, simulating this diffusion process. This is very similar to what we have in flow matching. And when we learn flow matching, we obtain some transport from P0 to PT, but it is deterministic. Yes, in this case, it is stochastic because it is a diffusion bridge. So for each point, you have some corresponding distribution. What we can do next? We can do next exactly the same thing as was done with rectified flows. This model learned on the first step defines some correspondences between data. So roughly speaking, some coupling between two data distributions. And we can use this coupling as an input to our training of our bridge matching model on the next step. Like we did in flow matching. We had some coupling obtained from our previously trained model. We use it for training the next model. So we train the next model on this coupling. we obtain some diffusion process which has some correspondence between input samples and target samples, and we can repeat this process many times. Exactly the same way as in flow matching. Nothing really changes. So to train a next model, you need to change the input distribution which you put to your training. Yeah, so now the distribution, it becomes the distribution obtained by the previous model. Yes, and to simulate samples from this, unfortunately, you need to unroll this entire previous diffusion process, like in flow matching. So nothing special changes compared to this, except for the fact that you work with diffusions now, not with ordinary differential equations. And surprisingly, this procedure converges. Well, not very surprisingly, right? Because when we talked about rectified flows, I gave you a result explaining that it converges to some ordinary differential equation with straight trajectories. In this case, the convergence is even more clear, like where it converges. So surprisingly, this model, when you do multiple bridge matching iterations on top of previous iterations, it converges to a particular diffusion process which defines a special coupling between two probability distributions, input probability distribution and target probability distribution. And this coupling is called the entropic optimal transport coupling. What is basically that? Basically, it is a coupling, so joint distribution with marginals, with input and target marginal distributions, that minimizes this objective. What is this objective? So this is called the entropic optimal transport objective, and we will see it in a more clear way in, I guess, 2 slides. So which does the following. So you need to find a coupling which minimizes some like cost function which defines the correspondence between input and target samples. And this cost function is defined by the logarithm of the density of your process, of your prior process, with which you do this bridge matching procedure. And this is some term which is usually called the entropy regularization. This is the differential entropy of your joint distribution on input and target samples. So it may not be very clear, like what are the properties of this coupling? Why this is meaningful? So what can I derive from this? Yeah, but in one particular case, it is very clear what it does, what this coupling does. So if we take as a prior process for our iterative bridge matching procedure the Wiener process, basically the Brownian motion with some variance, square root of epsilon, then this coupling to which the model converges is the entropic optimal transport coupling for the quadratic problem. So roughly speaking, we would like to find such a correspondence between input and target samples such that the target sample is as close as possible to the input sample in the sense of L2 norm, yes, and L2 norm squared, I mean, yeah. When we work with images, yes, this means that L2 pixel-wise correspondences between two images. Well, minus some entropic regularization term. Usually this entropic regularization is considered as some kind of addition, yeah, just to make it work better. But so these two examples, what it shows? It shows how this entropic optimal transport problem for the quadratic cost looks like. Why, you may ask, why this quadratic cost appears here? Why is this square? Because in this formula, we have to consider for our prior process Q the distribution of the endpoint given the start point. And for the standard Wiener process, this is just the normal distribution. So when we take the logarithm of this, we obtain this square. So this is an example how this looks like. So if you have simple two-dimensional distribution of Gaussian, this is in green, and this is Swiss roll, and you try to learn a diffusion bridge iteratively from Gaussian to Swiss roll. What you obtain? You start from some initial process, which is, well, I guess it's just independent. Yeah, so you sample one point, sample another, connect them with from bridge somehow. Then you do these iterations, and in the end you converge to the coupling, which transforms your green distribution to your orange distribution. And what this image shows, it shows the result of the translation. And these green points are just some chosen, some selected initial points from green distribution. And you see that, like, when you do this, like, transport from Gaussian to Swiss roll, well, the transport starts at some points and it ends at some points which are close to the original points. So roughly speaking, this transport tries to maximally preserve the content of the point, like coordinates, in L2 sense, L2 squared sense. Yeah. Of course, when we talk about application of this for images, yeah, this is not always optimal, because L2 pixel-wise correspondence for images, well, from computer vision, everyone knows that this is not always the best thing, right? Nevertheless, it can be used sometimes. Also, the authors of this paper related to diffusion Schrödinger bridge matching is called like iterative diffusion bridge matching, let's call it this way. They apply it to some super resolution problems related to physical fields. Yeah, well, where this L2 correspondence might be reasonable. Yeah. Also, they show some model examples how you can do domain translation on unpaired data. What they do here, for example, they consider the domain of like wild animals, the domain of cats, and do this like cat to wild and wild to cat and so on translations. These are like standard model examples, well, where people usually test such kind of algorithms besides some particular applications. Of course, this procedure of iterative bridge matching has the same problems as the procedure of iterative flow matching, like rectified flows. Yeah, it accumulates the errors because you usually trained your next model on the previous data obtained from synthetic data from the previous model, and so on. You need to do simulations to generate new data for training using the previous model, and so on. But surprisingly, for diffusion bridges, there is an extension of this diffusion bridge framework, which allows learning kind of two-sided framework when you learn both forward model and backward model, which helps to alleviate this issue of error accumulation. Yeah, I just give you this for information. I'm not going to discuss this in detail today because it is quite of a lot more complex, but you should know that if you want to apply diffusion bridges for unpaired domain translation, you should use not like one-sided training procedure when you train model like from left to right only, but you should consider its extensions when like both forward and backward models are learned. Also, we have a paper about this. Originally, this was proposed in diffusion Schrödinger bridge matching paper by some guys from Google DeepMind. Yes, we created some extensions explaining how this theoretically can work to alleviate issues of this error accumulation and so on, and why it actually holds. Yes, and I guess the final thing which I'm going to tell you right now is very, very briefly, yeah, because we are already running out of time, is that in fact this bridge matching framework has a lot of extensions. First of all, when we talked about flow matching, I told you that if you want straight trajectories for flow matching, there is no need to do many iterative flow matching projections. Yes, so theoretically we developed some way how to obtain straight trajectories in just one projection. Yeah, it was called optimal flow matching. In fact, the same can be used for bridge matching. So there is a paper, our paper, which is called Light and Optimal Schrödinger bridge matching, which tells you that, okay, you can obtain this optimal projection which converges to entropic optimal transport in just one step. Yes, if you consider specific parameterization and so on. Secondly, all these bridge matching methods, they all suffer from the same problem, that still to generate new data, you need to model your long diffusion bridge. You need to simulate it step by step by using some scheme like Euler Maruyama, and so on, which is complex. Interestingly, you can redefine the bridge matching procedure not using diffusion processes and not in continuous time, but using just transition kernels and in discrete time. This helps to build different algorithms which can do this bridge matching, but with much faster inference. So the time required to generate new data, yes? And instead of, say, 100 steps, which is usually needed to model this diffusion bridge generation process, in standard models, you can do it in just several steps by considering so-called discrete procedures for diffusion bridge matching. Okay, so finally, I think I'll now go to conclusion. Yeah. So what we discussed today. So actually, what we discussed today is just an extension of flow matching. Yeah. You may ask, why it is needed? Why flow matching is not enough? Why I'm telling you about all this? The main point is that flow matching, okay, if you want to build some generative model for data, yeah, you usually need some source of noise, yeah, and this source of noise in flow matching, when it is applied to image generation, is just given by construction. You start generation from noise, and you end at data, right? However, if you try to apply flow matching to some data translation problems, domain translation problems, yes, in many cases, there will be no source of noise, yeah, because you just have data and other data, and you need to do some generation. If you try to apply flow matching, for example, like for unpaired case and so on, it will not work. Usually, flow matching just does not work well when you consider generative models for data translation problems. And bridge matching, because it kind of artificially inserts noise to the training process, yeah, you connect points with some bridge, with some noise. Yeah, it kind of artificially adds noise to the training procedure, and it usually works better when you talk about domain translation problems. So roughly speaking, diffusion bridge models, they can be considered as a specific extension of flow matching specifically designed for domain translation problems. You can use it in conditional regime, in unconditional regime. You can apply it to paired and to unpaired data. And in fact, it is, yes, it is an extension of flow matching in the sense that flow matching is just this one particular case. So that's it. Questions?
Thank you for your presentation. I got two small questions. First of all, about notation in the presentation. What does it sub-index of U and D means for X? I suppose that there is a slide with a, yeah.
Well, it's just like 2 points, like upper point and up and down.
Okay, I got it.
Just separate them.
Okay, and the second question, more about ideologically, it's about the thing that's, for example, I suppose that for diffusion models, the inner geometry and topology is not preserving. And what if we combine, for example, learning into manifolds, as for example, you told about resolution enhancement task, and from the assumption that a lower resolution could be a submanifold of higher resolution, what if we combine denoising and projection into tangent space?
So there are a lot of works related to just diffusion models and flow matching on manifolds. Yes, some Riemannian flow matching, Riemannian diffusion models, and so on. Well, I haven't seen works which do diffusion. Well, I think, yeah, I think there are some diffusion bridge works for these manifolds as well. So it is just possible, but you need to just extend this theory a little bit. There are already some papers doing this, I think.
Thank you.
Thanks for your talk. My question is concerning the interpretation of the unpaired domain translation. There is indeed a very beautiful optimal transport interpretation, but as we know, it only supports the quadratic cost in all known efficient algorithms. And indeed, we can, for example, believe that L1 cost is unreachable and other distances. But what about the labels by which the distances are computed? I mean, if we just compare images pixel by pixel, that would be not a very meaningful distance. If we, for example, are doing diffusion in the latent space, it might be a little bit more reasonable. But what about the general case? If we are going to do the diffusion in one space, and for the pairing to use some distance in other space. For example, if we are going to use some feature extractor of the images during diffusion. Are there any works that do this? Because actually L2 cost in the exact space we're doing diffusion seems very restricting. Thank you.
Yeah, it's a very nice question. So a short answer is that within this framework, the framework of diffusion bridges, you are limited to using only those costs for which you can design a prior process for which it will, so basically the cost will be minus logarithm of this transition of the process. Yeah, so this can be, for example, L2 costs and some other costs. I'm not even sure that L1 cost fits here because I'm not sure you can design a process which will yield you L1 transition. But if you want to consider more general cost, you need to consider different methods from optimal transport, like neural optimal transport and so on. Within diffusion bridge models, just arbitrary costs are unfortunately not supported. And I'm not even sure that it is even possible to use them here.
Well, is it easy to see that if we add to the vector which we are diffusing some other features, for example, the label features by which we are going to compute the distance with higher amplitude, for example, and the L2 distance would be dominated by the features we are going to compute distance by, and our features would be diffusing to.
So you want to construct some prior process for which you will add some features, whatever inside. This is what you ask?
Yeah, more or less.
Okay, this is very tricky because, okay, you can construct very general like prior process, but to make this framework work, you need to have all these properties for specifically you need to be able to efficiently compute the diffusion bridge for this process, sample from this process, compute the score function and so on. And if you consider just some arbitrary process, not say linear process, and this becomes a very challenging thing. So if you add some features inside your drift function and so on, this will make everything not analytically tractable, and you will have to develop some more efficient.
I mean, it's still the Gaussian process, but to make the process not over the actual objects we are going to generate, but over the concatenation of them and some other labels.
Okay, so well, I think so. The problem is that here you need not only arbitrary Gaussian process, but you need this process to be Markovian as well. So the only as far as I remember, the only processes which are simultaneously Markovian and Gaussian are Ornstein-Uhlenbeck processes, and more or less like these are the main variants. Maybe this bridge matching and Markovian projection can be extended for non-Markovian processes, but I haven't seen such papers.
Okay, thank you.
Thank you for the lecture. It was convincing. In the part about iterative bridge matching, you say that the model learns from, it accumulates an error because it learns from previous model output. Does it happen during training process or during inference process?
Well, after the first training, your model is not perfect. That's it. So when you do inference and when you generate something by this model, it is not the true distribution which you generate. That's it. So this is why when you train the next step, you already train on something different from true data.
But is it possible to implement additional data in these steps between to improve the quality of the model?
It's an open question. So far, I do not know any algorithms doing this. Well, it can be done if you do this procedure which I mentioned, but I did not explain, when you do two-sided bridge matching procedure. Yeah, so this first paper explains this. And it will help to prevent error accumulation, yeah.
Okay, thanks.
But within the context of like one-sided, I do not know how to incorporate this data.
Thank you.
Mm-hmm.